Welcome to the 11th tutorial session of problem solving through programming in C. This is a SWAYAM course floated by Professor Anupam Basu from Department of CSE, IIT Kharagpur, and I'm Siddhant. I'm the TA who is in charge of taking these tutorial sessions where we will discuss some concepts and some sample questions which will help you with the final exam and the assignments. So, this session is geared towards week 11. So in week 11, we looked at the Lagrange interpolation method, and also we looked at the integration method, which is the trapezoidal rule. And also we looked at how to solve differential equations using the Runge-Gupta fourth order method. And then we had a look at recursion again, and we learned a new concept called structures. Okay, so let's go and solve a few questions related to that. Okay, are you able to see the questions properly? Yeah. Okay, so let's look at the first question, which is this. Uh, so basically, it's about the interpolation method or the Lagrangian interpolation. So given that we have two data points, f of a and b f of b, what would be the linear Lagrange polynomial f of x that passes through these 2 points, right? So this is a direct question. So we know that if we have these 2 points and we are supposed to write a Lagrange interpolation among them, so we can write f of x is equal to L0 of x into f of a here, because and then L1 of x into f of b, right? These are the 2 points. Now what is the formula for L0? L0, the formula is x minus b by a minus b, and for L1x it would be x minus a by b minus a. So if you just put this L0 and L1 in this equation, so what do we get? So x minus b by a minus b into f of a plus x minus a by b minus a into f of b. So it's option D. Okay, so I guess that's straightforward. So let's actually solve a question um, using this Lagrange polynomial method. So it's an interpolation method. So that means if you know some values of points, say there is some function f of x, and you know the values at a, b, and c, and you want to calculate the value at d using the values of a, b, and c. So this is what is called interpolation. Okay. Now here we know the values of the function f of x at x equals 10, 15, and 20. The respective values are given so, and the polynomial also, you can define it in a similar manner. L0 of x into 3 plus L1x into 5.2 plus L2x into 6.8. Now the question asks what is the value of L1 of x at x equals 18. Okay, so what would be the formula for L1 of x? So here L1 of x is related to this 15 x 15 f of x 5.2, right? So we are at 15 and we'll write the form with the other values apart from 15, and then right, this is the form for L1 of x, right? Similarly, if I had to write L0 of x, it would have been x of 15 and x of 20 divided by 10 minus 15, 10 minus 20, right? So okay, now what it is asking that the value of L1 of x at x equals 18. So basically here we need to put x equals 18. So if you put that, what do you get? 8 into minus 2, right? 8 into minus 2 by 5 into minus 5. So how much is that? I think it will be around 0.64. So option A is the correct answer here. So do you understand how do we do this? Like how do we calculate the value of L1, L0 and L2 in this question? Alright, now let's look at another question. So here the x is defined at 10, 15 and 20, and f of x, the respective f of x values are given here. So the Lagrange polynomial looks something like this, which is f of x L0 of x into 19.45 and so on. Okay, so the question asks what is the value of f of x at x equals 12. So for that, first we have to write the equation for L0 of x, L1 of x and L2 of x. Then we have to calculate the values, put the values in this equation and find out when x equals 12 what is the value of f of x. Alright, so let's just write L0 of x first. So L0 of x is related to the x equals 10 point. So our Lagrange multiplier, so this part is the Lagrange multiplier, right? So this will be x minus 15 into x minus 20 by 10 minus 15 into 10 minus 20. What will be L1 of x? L1 of x will be x minus 10 into x minus 20 divided by 15 minus 10 into 15 minus 20. Similarly, L2 of x will be x minus 10 into x minus 15 divided by 20 minus 10 into 20 minus 15. Okay, now we calculate each of this putting x equal to 12. We have to calculate each of these values, and whatever values we get, we put it in this equation. So this value we just put it here, this value we put it here, and this one just yeah, and this one we just put it here. A and B, sorry, A and B as in, like, what are you? Okay, A and B, regarding the previous, this A, B, C that I was saying. Okay, so here basically it's not just, so here there were 2 points in the question number 1. On this page there are only 2 points that we had, so the equation was something like this. But when we have multiple points, we have multiple data points, the equation will not be this, rather it will be basically here L0 is concerned with x equals 10, right? So the equation will be x minus, so instead of x minus b, it will be all the x minus all the points that apart from 10. Okay, so here we are at 10 for L0, the multiplier we are at 10, and so we write x minus 15 into x minus 20. Then the denominator part will have so there we wrote something like this, right? X minus b by a minus b into f of a, right? So just ignore this part for now. So this is the Lagrange multiplier part, right? So now here in this question there is actually a, b and c, and we are at a. So in that case the Lagrange multiplier has to be written as x minus b, x minus c by a minus b, a minus c. Okay, do you understand? So yeah, this is, now we are at a. Similarly, when we are at b, okay, so L1 of x is related to b. So when we are at b, we write x minus a, x minus c by b minus a, b minus c. Alright, so that is what we have done here. So we calculate all of this, you can calculate all of this and put it into the formula here for the polynomial, and then calculate the final answer from here. I think you will get the final answer to be 15.20 if you calculate it correctly. Uh, you will get the answer to be 15.20 for like the value of f of x at x equals 12. Okay, so you just put the value of 12 here in all these three equations, and whatever values you get, you just replace them in the f of x polynomial equation that is written in the question, and then you get the value of f of x at x equals 12. I hope that's clear how to use the Lagrange polynomial. It's just a bunch of calculations that you have to do. Otherwise, the concept is fairly straightforward. Um, any questions? Uh-huh. Okay. So if you have A, B, C, and D, these are the data available. That's what you're saying, right? These are the data available, and I need to find L0 of x. So I'm assuming that L0 of x is related to A, okay? I'm writing it at point A. So it will be x minus b into x minus c into x minus d divided by a minus b into a minus c into a minus d. Is it clear? So how this is, we are just going on increasing this, right? So here it was a and b, here it was a, b and c, here it was a, b, c and d. So this is how you will keep writing. So here there will be L1 of x, L2 of x, L3 of x. Okay, this will be like x minus a, x minus b, x minus c, all divided by d minus a, d minus b, d minus c. Okay. All right. So okay. So next we'll look at the trapezoidal rule. So trapezoidal rule is used for integration. Like you want to do some numerical integration, so you can use the trapezoidal rule. Okay. So how does it work? So let's say you have some function f of x. Okay. So this is say some function f of x. Instead of this, let me say this is f of x. Okay. This is now we want to calculate what is the area under the curve. So basically, if you are integrating f of x dx from a to b, where a is this and b is this, okay, and this is f of a, this is f of b, right? Now you want to find out this integration f of x dx from a to b. Now that means you want to calculate this area under the curve between this, right? So this area under the curve. So what trapezoidal rule says is that if I am considering that one segment trapezoidal rule. Okay, that means what I'll do, I will say that this is a trapezoid. So I'll say that this, I'm assuming this to be a trapezoid like this. Okay, this is the trapezoid. So it's roughly, I mean, it can be a bit different. This is one segment trapezoid. Okay, so one segment means between A and B there will be only one segment. That is what it means by one segment trapezoid. If I had to say about two segment trapezoid, then there would be one trapezoid from A to A plus B by 2, and then again one trapezoid from A plus B by 2 to B. So this is two segment. This is two segment trapezoid. So here this is one segment. Okay, so in one segment trapezoid, so what, how do we write the formula? How do we write the formula for a trapezoid? Like the area under the curve for a trapezoid, it will be half into b minus a, that is this, into f of a plus f of b, right? So the sum of the parallel sides, right, and the sum of the parallel sides in multiplied by this height, which is b minus a, multiplied by half. So that is the area of trapezoid. Okay, so area of the trapezoid. Okay, now let's just keep that in mind, and let's try to solve this question. So we have f of x here. F of x is x into e to the power 2x. Okay, and we have been asked to use a one segment trapezoidal rule. That means okay, so that means this is basically going to be our case. So one segment. Now, if there is one segment, and here this is a and b, which is 0 and 1.5. So we just simply put the area. What is the area? Half into 1.5 minus 0 multiplied by what is the value of this at so value of f at 1.5 plus value of f at 0. Okay, so how much is it going to be? Can you calculate it quickly? No, which one are you calculating, the first one or the second one? Yes, so this will be 22.596. So this will be answer for this question. But yeah, I mean the answer that you gave is correct for this question, the second question. So here also we just want to use one segment trapezoidal rule. So it's basically half into, here a and b are 3 and 0, so 3 minus 0 into the function here is x square into x to the power into e to the power 2x. So it will be f of 3 plus f of 0, right? So this will come out to be 5446.3. So here the answer is option A. But this question, the answer is 22.596. So I hope you have understood how to use the trapezoidal rule, the one segment trapezoidal rule. Now we'll see a question where we have to use this multi-segment trapezoidal rule. Okay. So so here you are directly being asked what is the area under the curve using the trapezoidal rule, and you are given values of x and y. Okay, so you will consider one trapezoid here between 1.4 to 1.6, one trapezoid between 1.6 to 1.8, one trapezoid between 1.8 to 2.0, and one trapezoid between 2.0 to 2.2. Okay, so what will it be? So let's calculate that. Half into, so 1.6 minus 1.4 multiplied by the values, which is 4.7428 minus 4.3215. So the value, so this is basically f of x. Okay, sorry, this would be a plus. Okay, so 1.6, so first trapezoid 1.6 and 1, the bounds are 1.6 and 1.4, a and b, and the corresponding f of x values are 4.3215 and 4.7428, right? So we write the area of the first trapezoid half into 1.6 minus 1.4 into the sum of the values f of a and f of b. Now similarly we add with it the second trapezoid. Second trapezoid is 1.8 minus 1.6, okay, and 4.7428 plus 5.5205. Similarly, the third trapezoid now, the third is 2.0 minus 1.8 multiplied by 6.0525 plus 5.5205. Okay. Now then the fourth trapezoid is 2.2 minus 2.0 multiplied by 6.0525 plus 6.8762. So this will be the total area under the curve using the trapezoidal rule. Now if you calculate this, the answer will come around to I think so it will come around to 4.3829. You can verify that, probably you can check this out whether this is correct or not. So but I think that is what the answer will come out to. So yes, yeah, I mean yeah, probably this is the closest. I mean Have you considered up till 4 decimal digits? Okay, okay. So maybe, I mean, this is the closest one. Even if you get 4.37, okay, so this is the closest answer, right? Closest option here, because everything else is 5, 6, 3, and so on. So this is the closest option. So that is what is going to be your answer. You can calculate it and check. Maybe it will vary a little bit here and there, but that is the only option. This is the most correct option in this case, I guess. Okay, so this is basically we used kind of a 4 segment trapezoidal rule. Okay, we had this 4 segments, one from 1.4 to 1.6, one from 1.6 to 1.8, one from 1.8 to 2.0, one from 2.0 to 2.2. So we had this 4 segments and we use the trapezoidal rule on them to calculate the area under the curve. So let's use the same concept that we have just learned to do a trapezoidal rule with 5 subintervals. So basically 5 segments. Now our range is 2.5 and 4. Okay. So the first thing that we have to do. Are you able to hear me? I hope you're okay. Uh, right. So the first thing that we have to do here is we know the range 2.5 and 4. Now we have been asked to use 5 subintervals. So we will divide this range into 5 segments. Okay. And how do we do that? I think so. Basically, it's a difference of 1.5, right? So 4 minus 2.5, that is 1.5, and we divide that by 5. So basically 0.3. So our first segment will be 2.5 to 2.8, then 2.8 to 3.1, then 3.1 to 3.4, 3.4 to 3.7, and 3.7 to 4.0. So this will be our first trapezoidal, second trapezoidal, um, third trapezoidal, fourth trapezoidal, and fifth trapezoidal. So this will be our 5 segments. Okay. Now, okay. So the function here is ln of x. Okay, it is ln of x, and all right. So let's write the area under the curve. That is basically the trapezoidal rule. So the first trapezoidal, the first segment we will have 2.8 minus 2.5 multiplied by ln of 2.5 plus ln of 2.8. Okay. Next we will have 3.1 minus 2.8 multiplied by ln of 2.8 plus ln of 3.1. Similarly, we can write the third segment. Third segment will be 3.4 minus 3.1 into ln of 3.1 plus ln of 3.4. Fourth segment would be 3.7 minus 3.4 multiplied by ln of 3.4 plus ln of 3.7. Fifth segment would be 4.0 minus 3.7 multiplied by ln of 3.7 plus ln of 4.0. So these are the 5 segments. We will calculate the values at all of this, and then I mean it will come somewhere in the range of option B. You can check that out. So for all of these questions that we are tackling today, there will be a fair bit of calculation. So if you are giving the final exam for this course, I would recommend you to try out the online calculator. So there is a announcement that has come, I think couple of days back or something. You can see it on the front page of the course. So there is a link for a demo of the online calculator. So because this kind of questions will require you to calculate a lot of things, especially this ln functions would be there, you have to calculate a lot. So I would recommend that you try working a bit with the online calculator so that you can calculate it fast enough. Okay. So for this kind of questions, as well as I mean for all the questions, more or less all the questions that we will be covering today, there will be a fair bit of calculations involved. They are simple concepts, but there will be a lot of calculation. So Okay, for this question you just calculate this, and probably it will come to be in the range of 1.74 to 1.76. Okay, just verify that. All right, so is there any doubts regarding the trapezoidal rule? Okay, so basically we are doing a numerical integration using the trapezoidal rule. So the higher number of intervals we take, the better, like the higher number of segments we take, the more accurate answer you will get from the trapezoidal rule. If you take a single segment, that will have most error, because you see your actual function is something like this. This is f of x, and you are saying that I am going to take this part. Say you had to calculate a point like this area under the curve, okay, this area under the curve, but you are taking what, if you consider a single segment, then you are actually considering something like this, which is actually ignoring the curve of the function, right? If you are taking a single segment. Now if I take many small segments here, many small trapezoids here, then that can capture the segment, the curve, the that can capture the way, like you can see the concavity or the convexity of the curve much better if you use multiple of this segment. So the higher number of segments that you use, okay, higher number of segments will lead to uh, more accurate integration, more accurate numerical integration. Okay, so this is something to know if you're going to use it later on for any purpose. So you should know that you have to do a large number of segments and then add them up. Basically this is how you do it. I mean, here we used 5 segments. You can do for higher, and you can get a more accurate answer. Okay, so that was about trapezoidal rule. Next, we'll be looking at the Runge-Gupta method. So basically, Runge-Gupta method is used for solving differential equations, right? For solving differential equations. Now, how do we do that? So here we are going to use fourth order method, which basically means that its local accuracy is in the fourth order. Okay, so it is a very highly accurate method. Now, the first thing that we do when we get this, so this is a ODE. Okay, it's an ordinary differential equation that we have here. So first we rewrite it in the form of dy by dx equals f of x y, f of x y. So this is the form that we write it in. Okay, so if we write this equation, this ordinary differential equation in this form, what will it be? It will be y cube minus x square by 4, right? So this will be our f of x comma y. Now it is saying that x naught, like the x, the in the initial value of x, the initial value of x is x naught, and that is 0.5, for which the initial value of y is 2. So the value of y at this x value of 0.5 is 2. That is what we know. Okay, and we know the step size, which is h of 0.2. Okay, now we are asked to calculate the value of y of 0.7 using the Runge-Gupta fourth order method. So for if you have seen the lectures, you might remember the form of the equations, which you will have to remember if you want to solve this Runge-Gupta method. So here if I want to write y of 0.7, we already have y of 0.5, so we just need to go one step forward to get y of 0.7. So let me write the equation first. So y of 0.7 equals y of 0.5 plus h by 6 into k1 plus twice k2 plus twice k3 plus k4. right? So this will be the equation. Now what are this k1, k2, k3 and k4? So k1 I calculate it as f of x naught comma y naught. That means just put these values into this function. So how much will that be? This will be 2 cube minus 0.5 square by 4. You can calculate this. Then k2 will be x naught plus h by 2 comma y naught plus hk1 by 2. Okay. So similarly you can calculate this again with putting this y naught plus hk1 by 2 whole cube minus x naught minus h by 2 whole square whole divided by 4. So you can calculate this. Now k3 will be f of x naught plus h by 2 comma y naught plus hk2 by 2. Okay, and finally k4 will be f of x naught plus h comma y naught plus hk3. So you can calculate k1, k2, k3 and k4. Then you replace them in this equation. So you put all the values of k1, k2, k3 and k4 here. Put a h value of 0.2 as has been told. So the step size is 0.2. Now if you calculate this entire thing and put the value of this will be 2 plus this will be 0.2 by 6 into, you will get all the values here. Okay. Now if you do that, you will get a value of roughly 2.5546. So here you will get an option B. So all of these questions you have to take some time, carefully solve them so that you don't make any calculation mistakes. So try to calculate this out. So I'm just telling you the answers right now because the calculations will take some time for you to do. So you can do this after the session. I will share the PDF, of course. You can just have a look at the question again and try to solve it on your own and calculate it. All right. Okay. So so this Rangekutta method is basically a class of methods which is used for solving ordinary differential equations. Okay. Now this is a ODE that is given to you, right? This thing. This is a ODE, ordinary differential equation, and we have been told about a initial condition which is y at x equals 0.5 is 2. And using a step size of h 0.2, we have to calculate the value of y at 0.7 using Rangekutta fourth order method. Now when you get this ODE, the first step in Rangekutta method is to convert it to a form of dy by dx equal to f of x comma y. So I'm just going to rewrite this equation as dy by dx equals y cube minus x square whole divided by 4. So that is what I have done, and this is going to be my f of x comma y. Okay, now, and I know that the initial condition, what is the initial condition? X at x 0.5, y is 2. So now I write the equation for like increment by step size in Rangekutta method. So y of 0.7, y at 0.7 that we need to calculate. So here we already know at 0.5 what is the value of y at 0.5. At x equals 0.5, we have to calculate what is the value of y at x equals 0.7, and we have been told to use a step size of 0.2. So basically we just need to go one step size in order to get this. So we can write this as y at x equals 0.7 can be written as y at x equals 0.5 plus h by 6, so h is the step size, into k1 plus twice of k2 plus twice of k3 plus k4. Okay. Now this k1, k2, k3 and k4 are this functions of some x, y and h. So let us see what they are. So k1 is simply f of x naught comma y naught, that is the initial values that you had been given, so 0.5 and 2. Okay, now you calculate, once you calculate k1, you use that in calculating k2. So k2 is f of x naught plus h by 2. X naught is 0.5 and h is 0.2, and y naught comma y naught plus h k1 by 2. So k1 you have calculated, you can put that value here and then you recalculate this. So f of xy is y cube minus x square by 4. So you can calculate that again and find k2. So after finding k2, you again calculate k3, which is basically f of x naught plus h by 2 comma y naught plus h k by k2 by 2. So you use the value of k2 here and calculate the function, the value of this function f at x naught plus h by 2 and y naught plus h k2 by 2. So after you have calculated k3, you calculate k4, which is basically the function value at x naught plus h and y naught plus h k3. Okay, so then you calculate this. So k3, you use the value of k3 here and you calculate k4. So once you have calculated all k1, k2, k3 and k4, you just put the values in this equation here at k1, twice of k2, twice of k3 and k4. Put the values here, replace the value of h. So next you just calculate this, and if you do all this calculation, you will probably get an answer of 2.5546. Okay, is that clear how to do? Then you have to do it twice. Okay, so in that case, if h was 0.1, you would have to calculate y of 0.6 using this, like h by 6 and like k1 twice k2 twice k3 and k4. Okay, then you would have to calculate 0.7 using y of 0.6 plus h by 6 k1 plus 2 k2 plus 2 k3 plus k4. But here, while you are calculating this k1, x naught would be the value 0.6, okay, and y naught would be whatever the value is at 0.6. Okay, like whatever you get y of 0.6 from here, that will be your x naught and y naught. So you have to keep that in mind, that when you're calculating, say, in step size of 1.1 here, okay, and you need to reach, say, 0.7. So first you will calculate y of 0.6 using whatever process we just did. Okay, h value you will just take as 0.1. Next, while calculating h of y of 0.7, you will take y of 0.6 plus here h again 0.1, but this k1, k2, k3, k4, here you will take x naught and y naught as 0.6 and y of 0.6 respectively. Is it clear? Okay. Any further questions on Runge-Gupta method? Okay. Then let's go to something that we read a while back, that is bisection method. So why I have added the bisection method part here is because we were looking at different kinds of method, right? So we looked at the interpolation method, which is basically this Lagrange. So basically we looked at this Lagrange method of interpolation. We looked at method for solving ODEs, which is Runge-Gupta, right? We looked at Runge-Gupta methods. We looked at methods for integration, which is basically our trapezoidal rule. Now, why I have added bisection is because why do we use bisection? It is a root finding method. Like we have seen in the previous weeks, bisection is a root finding method. That means if we have a function f of x, we can find out where the function goes to 0. For what value of x the function goes to 0. So that is what we are gonna do right now to find the root of this function. So here the function f of x is x to the power 4 minus x minus 10. So the question asks us to do around 5 iterations using the bisection method, and they have given the two initial conditions, A and B. So first thing we do is we calculate f of 1.5 and f of 2, right? Once we calculate this, we will observe that one will have negative value and one will have positive value. You can check which will be which. I think this will be a positive value and this will be a negative value. You can check that out. So this is required, so that that means we know that our function gets to 0 in between 1.5 and 2. Okay, so let's do the first iteration. So if you do the first iteration, so what value do we have? Say c equals 1.5 plus 2 by 2, that is 1.75. Now you calculate the functional value at 1.75. Okay, and if it is positive, then can you calculate the value at 1.75 and these values at 1.5 and 2? Sorry, can you repeat that? Minus 2.37. So this is for 1.75, minus 2.37. And can you calculate at 1.5 and at 2? Yeah, like if you calculate exactly, that would be much more helpful. Minus 6.43 and at 2, four, right? Something like 4. So 16 minus 2, 14, minus 10, 4, right? So you can see that this negative value is closer to 0 than this negative value, right? So we will replace, instead of taking 1.5 and 2, we will take 1.75 and 2. So second iteration we will use 1.75 and 2. We calculate the midpoint of that. How much will that be? So basically 0.25, so 0.125, yeah, 1.875. Now we calculate the functional value at 1.875 and we check whether it's positive or negative, and accordingly we'll just replace that value, and then we'll go to the third iteration and we'll calculate the c again. So this will continue all the way till the fifth iteration. So by that time we will have, in the fifth iteration, whatever midpoint value you calculate, whatever value of c you calculate, that will be your answer here. Okay, and if you do that, probably you will get a answer of 1.86. Yeah, that is correct. So around 1.86 you will get. So if you do that till the fifth iteration, you have to keep going until the fifth iteration. So whatever value of c you calculate here, that is going to be your root, basically, or basically that is what the question asks, that you do 5 iterations of bisection and tell us the root. So that will be the root. Okay, now we'll look at another similar kind of question using bisection. So here the f of x is x cube minus 4x plus 9. Okay, now here you can notice that it has a few peculiar things. This question has not given you the initial conditions a and b, and it is asking particularly for the negative root. So that means you want to find the value of f of x. So it is a cubic equation, right? So it will have 3 roots. Okay, so because it's a cubic equation, it will have 3 roots. Now out of the 3 roots, we need to find the negative root. So that means we need to take our initial condition such that we will get a negative root. Like whatever value of x we finally get at, it should be negative, and accordingly the answers also you can see they are given at minus 2.5, minus 2.7 and so on. Okay, so in that case we have to try, when we don't have any initial conditions given, so we have to do a bit of trial and error, or if you can visualize the function, either will do. Either you can visualize the function somehow, and take some ranges according to that, or you can like you can take some trial and error. So say, let me seeing the options here, I would say let's try f of minus 3. How much does that give us? So minus 27 minus 12 plus 9, right? Minus 27 minus, oh sorry, plus 12 plus 9 minus 6, right? So this is a negative. Now let me try minus 2. So minus 2 would be minus 8 plus 9, so it's 9, right? So this will give us a negative root, right? Because this is negative and this is positive. So then there is a negative root between minus 3 and minus 2. We do know that now, right? So let us take this as our initial condition. So let's say a equals minus 3 and b equals minus 2. Alright, so let's start the bisection method then. First iteration, we'll calculate c. So minus 3 minus 2 by 2, which is minus 2.5, right? Now we calculate the function at minus 2.5. Okay, just check whatever this value would be. 3.375. So this is positive. That means it will go and replace minus 2, and it is closer to 0 than 9, right? So for the when we write the second iteration, we will now consider minus 3 and minus 2.5, right? And how much will this be? Minus 2.75, right? So f of minus 2.75, we have to calculate this value. Just check how much will this be. I think it will be negative. Just check that, and we'll minus 0.9. So this is 0.79. Okay, so this is getting pretty close to 0. So we know that we are close to our root now. So next what we do is we take this minus 2.75 instead of minus 3, because minus 3 was how much? Minus 6, right? And from there we went to minus 0.79. So we are getting close to the root now. So we'll take minus 2.75 minus what did we have? 2.5, right? By 2. This is how much? Minus 2.25 again. So 0.625, right? If I'm not wrong. Is it correct? Yeah. Okay, so we calculate now the value at minus 2.625. So yeah, calculate this. Probably this will be okay. So this is positive. That means it will go and replace minus 2.5. Okay, so in the fourth iteration, what we will do is we will take this minus 2.75 and minus 2.625. We'll take the bisection of this. So yeah, here you can see that the values, okay, there is the none of the above option, so you have to do this until it actually gets to one of these values. But the only option that could fit here would be this, right? Because this is within the range of minus 2.75 to minus 2.625. But because of the none of the above option, you have to go and do a few more iterations and check whether it's actually settling down at this. Or you can just calculate, you can just put this minus 2 point, like you have now seen that either it could be minus 2.706 or none of the above. So just put this value into this equation, right? And see if the value is coming out to be 0. If it is coming out to be 0, then this is your answer. So you can make a educated guess as to what the solution is, and you will see that this will come out very close to 0. So here the answer is minus 2.706. If you want to exactly calculate it, then you have to go for a few more iterations, but otherwise you can see that this range, only your answer can be only option B or option D. And option B, if I try out, if I put the value in f of x, I'll get a value very close to 0. So it saves us time basically. Okay. Yeah, so it's very close to 0. Okay, so it's should be fine. Otherwise, you can do the iterations out and check. If you are not, if you are not satisfied with that, then you can do a few more iterations here. You will converge to more or less this value. Okay. Okay, so minus 3 and minus 2, how did I take that? So basically here we wanted to have a negative root, right? So whatever value of x we got, it should be negative. Now I just saw the options here because this is a like multiple choice question. So I just saw the options here that all of them are minus 2 point something. So from that I just did a trial and error that what is the value of this function at minus 3, what is the value of this function at minus 2, and so on. Okay, so if it had say like positive roots, okay, you need to find the positive root if this function has any, then I would just blindly calculate first what is the value say at 0. Okay, so at 0 it has a value of 9, right? So it is already positive, so where it will get negative, let us check that. uh, yeah, a bit hard to say, just like that. Positive, we have to think about it a bit where to get the positive root, or if there is a positive root or not. That is one way. I mean, trial and error is just one way. Another way what you could think about, yes. Yes, you can do that. But sometimes the value will be, all of the three values will be very close. Okay, so in that case you have to do a few iterations and check. Okay, so putting the answers in the solution will work for this root finding. Okay, but you have to be a bit careful. Sometimes they might give some questions where the options are very close to each other, or it might be a numeric type question where they will not give any options at all. Okay, so you have to be careful regarding that. Okay, so one method is this trial and error to find the initial conditions. The other method is kind of visualizing the function. So let's say I have I have x cube here, right? So it would be a very like sharp function like this, x cube, right? X cube. Now minus of 4x. So minus of 4x would be something passing through the center, right? If I write f of x equal to minus of 4x, so it would be something like this, right? And plus 9. So whatever. Okay, now we just need to add up these two curves. So this is y equals minus of 4x, this is y equals x cube. Okay, now we just add up these two and then we add the entire thing and we shift it by 9. Okay, so they are meeting, currently they will meet only at x equals 0, right? So we are going to shift this function, we are going to like add these two curves up. Okay, let's see how that works. I mean, I'm trying to visualize the function as you are as well. So this will decrease a bit, but after some time it will, I mean, yeah, or you could consider this 9 minus 4x as a curve itself, right, instead of considering this 9 separately. So let's say instead of this I would say that let's say there is a y equals minus 4x plus 9, right? So that would have like at 9 it would be like this, and this would be y will be 0. Where will y be 0? That will be 9 by 4 roughly, so somewhere here 9 by 4. Okay, so we'll have a curve like this, something like this. Okay, it's very rough, I'm just drawing it just like that. So this is a straight line. Consider this to be a straight line. It's not very well drawn, but yeah. Or I can try to draw it with a bit more precision. Okay, now it went through something else. Okay, fine. So this is a curve which is minus 4x plus 9. This is a curve which is y equals x cube. Okay, now you need to add these two functions up, like these two curves up. Okay, and you need to comment on that. So you can see that it has a root somewhere here. Like if you yeah, it is going to be a bit difficult to say that, right? Hmm. The visualization method, it's not very, yeah, you can get stuck there. All right. Let's start with the blank slate. This visualization got pretty messed up pretty fast. Uh, yes, yes. That's what I was saying. I mean, that is one way, like the trial and error, or to just see the answers and get. But what if it's a numeric question, right? So it's still trial and error will work if it is like if you are easily able to calculate the function, you can do a few trial and error and get that done. But if not, then I would suggest that you can try to visualize the function a bit. Say it's a numeric type question. You can still do trial and error, but if you don't know where to start from, you could try to do a bit of visualization. So here I have this y equal to x cube function. The other, let me say it is minus of, so let me do this, okay, this function y equal to 4x minus 9. So this will pass through minus 9, uh, right, it will pass through minus 9, and where will it go? It will go to 9 by 4, right? Say 9 by 4 and minus 9. So you will, this will be your line. It might, so definitely it will cross x cube somewhere. Okay, so that will be your root, right? Probably, or maybe I'm doing it wrong. Can be either of the things. So yeah, I have to look into this. Let us discuss this at the end. It is taking up a bit of time. Yes, yes, which is the closest to zero. Which one? Minus 2 point? Yeah, that's what that is the thing, right? I mean, that's why I said that because none of the above is an option here, you cannot really comment on that. Okay, because maybe this will converge to a value of like you, at some point you will get the value of minus 2.706 here. Okay, so we don't really know, and that is where we will stop because it has just asked correct to three decimal places, and that will match with this answer. Okay, so we'll just stop there. We'll not go to the next iteration itself. Okay, so we don't know if say, because none of the above is an option here, I would still say that you have to do a few iterations more and actually calculate the answer here instead of just putting the value there and checking, because it will never be exactly zero. That's the problem with this, because the answers whatever will be given even in numeric type, it will never be exactly zero. Like the root, you will not be expected to find the root exactly. Okay, so it will always be some very small value, like 0.000 something. Okay, so you need to keep that in mind while doing that. And yeah, this visualization technique I'll just tell you at the end probably, because yeah, I'll have to also think about it a bit and actually plot it to see how it is looking. Okay, so let's look at that at the end. Okay. Oh, okay, now we have just the questions, programming questions. So first question is to add two complex numbers using a structure. So yeah, I'll just go to the code because it's pretty straightforward. So we use type def. and we use, so basically why I'm using type def is because I want to define this structure called complex. Okay, and I'm going to give it the tag called complex, so I can directly use just complex instead of struct complex whenever later on I want to use it. So I'm defining a user defined data type here. Okay, user defined data type, so that is complex here. And what is that user defined data type? It has two floats. One component is dot real and the other component is dot imag. Okay, so now I write the function complex. Why complex? It will just return a complex value, that is why. So I've defined this user defined data type. I can write now using this complex. I can just write complex add is my name of the function, and it takes two structures into the like as parameters, n1 and n2. Okay, these are again like user defined data types n1 and n2. I define a temporary value like using this complex temp, like you define int x, right, int n. Similarly I just write complex temp. Okay, because this now a user defined data type. Now I just add the real parts of n1 and n2 and imaginary parts of n1 and n2. Okay, and then I return this temp to wherever or whichever function is calling this add function. Okay, now in the main function what I do, I take the input from the user regarding the first complex number, the real and the imaginary part, and the second complex number, the real and the imaginary part. And you can see how I've done that using scanf. So I just defined n1 and n2 here, which are complex variables, and one n add, which will store the value coming from the add function. Okay, so this n add equals add of n1 and n2. So I just pass this n1 and n2 after storing the values through scanf in n1 and n2. So the two components I have accessed them as dot real and dot imag. So these are the two components, right? Real and imag, right? So every complex variable that I define will have these two components, n1 and n2. So similarly, this n add will also have like two components, n add dot real, n add dot imaginary. So that is what we are printing here. Okay, is it more or less clear how we are going to use the structure? The structure is a user defined data type, right? Okay, all right. Now the other thing that I want to cover is recursion, because we have not seen any question on recursion. So let's try to do this hailstone sequence. So what is a hailstone sequence? Let me write that down. So let's say we have a number n. If it is an even number, then we just divide it by 2. Or if it's an odd number, we multiply it by 3 and add 1. Okay, and this would be our subsequent hailstone number. All right, so this is basically the hailstone sequence. This is called the hailstone sequence. If the question asks something like this, it will be given like what the hailstone sequence is. In the question, it will be specified. Okay, you don't need to worry about that. Okay, now I need to write the recursion for this. Okay, and this goes on till n becomes 1. So this sequence um, goes on till n becomes 1. At the point that n becomes 1, this will stop. Until it is greater than 1, it will keep going. So it will stop. The last value of the hailstone sequence will always be n equals 1. Okay. So, alright, now let's try to write a recursion function for this. Okay, let's say first I just write a main. I say int num equals 15, because that is where I want to start the recursion, the hailstone sequence. And I will just say like get hailstone of num. Okay, I'll just call this. Okay, return 0. So this is my main function. Just I'm calling the get hailstone. I'll do the printing inside the get hailstone itself. Okay. Now let us write So I'm not returning anything from here, so it's a void function. Okay, get hailstone. Now the first thing is you need to know for every recursion there should be a stopping criteria. Here the stopping criteria is when n becomes 1, it should stop. Okay, so in other words, I can say that if n is greater than 1, then it will keep going, right? If n becomes 1, then it stops, but if n is greater than 1, if it keeps going again and again. So my condition, let me write if n greater than 1. Okay, what happens then if, say, at some iterative some iteration, uh, or some recursion step, n is greater than 1. Okay, so what do? We will check if n is a even or a odd number, right? If it is a even number, then what we are supposed to do, we are supposed to continue the hailstone sequence with n by 2. If it is a odd number, we are supposed to continue the hailstone sequence with 3n plus 1. So what I will do, I will just call get hailstone directly. With what? With n by 2. And if it is an odd number, I'll just call this get hailstone sequence with 3 into n plus 1. Right? And yeah, that's all. Oh, okay. The printing step. We have to do the printing step. So here it has to do the printing. The last one will be n equals 1. Right? That's why the sequence goes till n equals 1. So I'll just print everything outside, percentage d comma n. I just print n every time, whatever n comes to this code. So this, the last one will to be printed will be 1, and at that point there will be no more calls of get hailstone, and it will keep returning back. All right, so um, yeah, pretty much this is going to be uh, the algorithm for this. I think it's also pretty much the same that I've written here, I guess. Yeah, so I'm printing this. I'm setting if num is greater than 1. I check if it is an even number, then I call with num by 2. If it is an odd number, I call with 3 into num plus 1. Yeah, so this will print something like 15. Then 15 is an odd number, so it will be 45 plus 1, 46. Then it will come 23. Then again it's a odd number, so it will be 70, right? Then 35 and so on, like it will continue until it becomes 1. Okay, is this clear how I'm using recursion here? Okay, all right. Hmm. Okay, so that's actually all that I had for you today. So now I'll be taking questions if you have any regarding the previous week. Someone was asking regarding week 10, some question. Yes, okay. Let me. All right. I have to look at the question first. What is the question? So we have, so week 10, question number 10, right? Yeah. Okay. So we have a array A, which is 10 comma 12 comma 6 comma 7 comma 2, and we are defining I and star P, which is a pointer. All right. So let's have a look at this. Let me see if I can write this down. 10, 12, and 6, 7, 4, something like that, right? Something like that. 672. Okay, 672. So these are the different arrays. You can you still see the, like, can you see me writing? Let me. Sorry, I couldn't get what you're saying. Oh, okay, that's what you're trying to. Okay, I see. So that is your doubt. Okay, I think they will recognize this and they will give you points for it. So don't worry about it. There will be some kind of notice soon that this there has been a grace point for this. So it's fine. Okay. Yeah, yeah, I got it now. Okay, so this is just a problem with the options, not with the question itself. Okay, fine. Yeah. So were you able to solve this question? All right. Anything else that you wanted to ask? All right. All right. All right. That was not a good question to visualize actually, but yeah. Let us try that again. Okay. So this is a cubic equation. So it should have like three roots, right? So I checked this out and it turns out that it has only one real root and two imaginary roots, because imaginary roots will occur always in pairs, right? Like conjugate pairs. Okay, so one real root, which is the negative root that we are finding in that question. So anyway, so we have this x and so this is y. First thing is just this, yeah, y equals x cube. Okay, now the other thing, so I am writing this too, which is 4x minus 9, right? Now I'm going to subtract this. So it will be like y equals x cube minus 4x plus 9, right? So this is going to be our function. So that's what my intention is. Uh, okay. Just a moment. All right. Let's see how this visualization goes. So technically, what should happen is that let me use some other color here. Say green. Okay. Now next I will just draw y equals 4x minus 9. So this passes through minus 9 somewhere around here, minus 9, and some 9 by 4, so roughly 2, right? 2 point something, so 9 by 4. So I have this function which will, like, yeah, maybe, yeah, it's a bit distorted, but we'll see. So this is going to be like the function. So you can see that there will be one root here. Bad color choice. So uh, okay, okay, yeah, yeah, yeah. Okay. Right. So it should deduct it, right? Uh, yeah. Basically, that means when these two are meeting each other, that is the root, right? So one curve I have drawn is x cube. The other I have drawn is 4x minus 3, 4x minus 9. So basically, whenever these two values are the same, that is where our root is it not? Yeah. So and we can see that if we just roughly we have to plot it a bit to visualize. So we have x cube, which is pretty sharp here, and then we have this, which is y equals 4x minus 9, um, and it will meet up somewhere in the negative part. Okay, now somewhere is a very fancy word. It's we have to see where exactly it will meet. For this, even if you have visualized that it's a negative root, so this is good for visualizing where it can have a positive and where it can have a negative root. Say if it is a numeric type question, so what I was saying earlier, say this had been a numeric type question and it would have had like multiple possible roots because it's a cubic, right? This particular example does not have multiple real roots, but say it's a quartic equation or something, so there might have been two real roots or something, right? So one positive, one negative. So it would this visualization technique will actually help us knowing like where it can, you know, where you can have a value, okay, possibly. So for example here, if it again after 9 by 4, if there was a meeting of these curves, say, then you could say that 9 by 4 might be one of the, lower or upper limits for the uh, for the initial condition. So like kind of visualizing, but for most of the questions, it will be actually better for you to do a trial and error method rather than a visualization method, because visualization, depending on how good you are at drawing graphs, it might take more time. Like if you are like me, which I take a lot of time in drawing graphs, so it's better for me to do trial and error method rather than visualization method. So if you ask me to find the initial conditions for bisection, I would just try a few, few random values here and there to calculate the initial conditions for the bisection method. So that would be me. But I mean, if you are really good at drawing graphs and all the functional shapes and so on, you can go ahead and try to visualize. But there can be pretty, tricky functions, like you can have 4x e to the power x, or you can have like x into cos x, like those kind of functions. So visualization might be a bit tricky in this kind of functions when you have this x into cos x into sin x, these functions. So I would say use it carefully. Better to go with a, like, in if you are in a time crunch, you don't have enough time, I would say just put in, and you have a calculator available with you, right? So just put in some trial values and get things done instead of trying to visualize things, right? Because no one is going to see how you have solved it, rather what is the answer. So I would recommend you go with the trial and error rather than a visualization technique. Okay. Okay, so this one that I was talking about. So A is 10, 12, 6, 7, 2. This is the array. And we are doing P equals A plus 4 or something like that, if I remember correctly. Um, P equals A plus 4. Then we have a for loop going from I0 up till I less than 5, and we are printing P of minus I. Okay. Okay, we do this, then we do for I 0 to 4. I'm just writing the pseudocode, okay? Then we print P of minus I. Okay, so this is what we are supposed to do. Alright, so A plus 4. So now when you're defining this array, A is pointing to the first element, right? So like if you say only A, it's a pointer to this first element of the array, and you have a pointer p, which is you have defined as a plus 4. That means plus 1 plus 2 plus 3 plus 4. P will point here. Okay, a plus 4. This is a plus 1, a plus 2, a plus 3, a plus 4. So p equals a plus 4. So p will point to 2. Now when you are printing p of minus I, what does that do? That basically, if I have to write this in pointer notation, so pointer notation really helps when you are doing this kind of stuff. So you can write this as star of p minus I, right? This is equivalent to star of p minus I. Now for the first case, what is p minus I? Like iteration 0, when I equals 0, star of p minus I will be star of p minus 0. P is pointing to this, minus 0 means same. So 2 will be printed. Then for I equals 1, P is still pointing here, and P minus 1. P minus 1 means it will, this is P minus 1. Okay, this is P minus 1, this is P minus 2, and so on. Alright, so P minus 1, so we go up, it will print 7. So then it will print 6, then it will print 12, then it will print 10. So basically your answer will be 2, 7, whatever comma or space, whatever is there, it will be 2, 7, 6, 12, 10. So this is going to be your answer. Is it clear? Okay. Any other questions that anyone has regarding any of the assignments from the previous weeks and so on? Do structures have continuous memory locations? Okay, let me answer this in this way, that you can define an array of structures. Okay, so if it is an array of structures that you have defined, so okay, so here, like, I have defined this array, this structure called complex. I could have defined, sorry, sorry, I can't hear your voice. So let me answer this question first. Yep. Yeah, just wait a minute. I'm trying to answer this question first. Uh, okay, so if it is a array of if it is an array of structures, say I define an array complex of size of number of elements 10. Okay, so that means it will define an array of structures which is complex. Okay, this particular structure which is complex. Okay, so it will give you a contiguous memory location of that. Okay, so you will have, and if I define only one variable here, say n1, it will have a continuous, it will also be saved in a continuous manner. So here both are of type float, right? So you will have like 4 bytes and 4 bytes. So together it will be stored like this. This will be the real and this will be the imag. But now the question is, what happens when there is uneven data type, like unequal data types? Okay, so let's say I have one character, say A, and one float which is B. Okay, let's say this is my structure. So in that case, you will see that it will not be like, if you, the size of one structure variable, if you calculate using the size of function, here it will be 8 bytes. Okay, but here it will not be 5 bytes, it will not be 5 bytes, it will still be 8 bytes here. That is a thing with structures. So there will be 3 buffer bytes. Okay, so let's say, okay, one more, yeah. So you have A being, this is occupied by A character, occupying 1 byte, right? Then the next one will only start after this 3 bytes. This 3 will be buffer. Then your B will be saved here. Then again the next character A will be stored here. And then again 3 buffer, and then B will be stored. So this is how it, so this is one structure memory. Like one variable will be this much. So it will still be 8 bytes. There will be some buffer location. So the size of a structure is greater than or equal to the sum of its individual components. Okay, it can be equal when both of these are of the same type or occupy the same amount of memory. For example, if float and int you have used, both are occupying 4 bytes, that is fine. So you will have, the size of its components will be 8 bytes and size of the structure will also be 8 bytes. But in a case where there is uneven, like variables of different components of different sizes, say character and float, then the size of the structure will be greater than the sum of its individual components. But yeah, to answer your question, they will be stored continuously, but sometimes this buffer comes into the picture. Okay. No, we cannot. We cannot utilize. That is wasteful. That is why, unless you absolutely need to use a structure, don't use a structure. Rather, go for a union if you want. Um, because if you just need only to save one component at a time, then it's better to use a union rather than a structure. And yeah, I mean, this is the problem with structures, that they have this buffer bytes which do nothing basically. So I would say structures are good when you have similar kind of data types, like occupying similar bytes from the space complexity viewpoint. But if you have like very uneven data types like character, float, boolean, whatever, so then structure is not very lucrative to use from the space requirements approach. Yeah. All right. Okay. Yes. So someone else was asking something regarding pointers. Can you again repeat the question, please? Okay. If not, then anyone else has any questions regarding any of the previous weeks, any of the previous week's assignments? Okay. If there is not, then we can close this session. Yeah. So there goes the link. You can see the previous week's PPTs and recording there. The links will be there. And yeah, if you have any queries regarding today's session, you can just ask me right now, or if with any of the assignment questions from previous weeks, you can ask that as well. If not, then we can just close the session. All right, then let's close the session here. Thank you for joining. We'll meet for the last week next week for the last week's lectures, week 12. Thank you. So next week, Tuesday 6 to 8, that will be our next class. All right, thank you for joining. Have a good night.